And now we are in lesson 13, geometry. We are building a volume formula for a pyramid. Lesson 12 and 13 really go hand in hand, so I'm happy we're doing them together. Our little warm-up, cover your bases. 2 solids are shown. For each solid, draw and label a prism or cylinder that has a base congruent to the solids and a height equal to the solids. So for form A, I'm not going to build a cylinder because the base of this is a rectangle. So I'm going to go ahead and build a prism, rectangular prism. So I'm using a highlighter because I know I'm not going to be extremely good at this, but really we're doing that, where I can say my height is 25. Okay, this side is 32. Oh, it doesn't look 32, does it? And that side is 20, where the volume of this would be 20, the volume of the base, 20 times 32 times the height. Sorry, the area of the base, which is 20 times 32, times the height, which is 25. Okay, I don't actually need to calculate it, but what we're showing there is the volume of the rectangular prism is length times width times height. And we're going to compare that to the volume of the rectangular pyramid here shortly. All right, now this one. I wish I were a better artist. So here I need to draw a cylinder with a radius marked 7 feet. I can't do a right one. Well, I could. I mean, if I just did right here a right cylinder with a radius of 7 feet and a height of 10 feet, that would work. Okay, feet. I'm not gonna, what I was worried about, what I'm not very good at, is drawing an oblique one. Okay, don't judge me. Okay, I have a radius of 7 feet and a height of 10 feet. Not bad. The volume here would be pi r squared times h. Cool, let's move on. Again, this would have been a fantastic lesson to do in class together. But here is a triangular prism. Suppose we split the prism into pyramids like the ones you built earlier. Okay, earlier they mean lesson 12. The nets, okay, that we built by hand. The first pyramid is split off by slicing through points E, D, and C. Okay, I can't even draw on to show you that. The remaining part of the prism is sliced through B, C, and D. Okay. Suppose we split the prism into pyramids like the ones you built earlier. These are the instructions from the last slide. The first pyramid is split off by slicing through those points, which is right here. The remaining part is slicing through the other points, which is B, C, and D there. And then we have the leftovers. Oh no, that's this one. Okay, so they've sliced the pyramids into pieces. We went from the previous slide, which was a triangular prism, into 3 pyramids. Okay, you realize we went from triangular prism to 3 pyramids. All right, now this is where I think we're just going to have to jump to the end of the lesson. We're going to try to do this together during our Google meeting. So using the pyramids you built, compare pyramids 1 and 3. think of the faces marked pyramids 1 and 3 as the bases of the pyramids. These triangles are the two bases of the original prism. How do the areas of these two bases compare? The areas of these are equal. That's not a Q. The areas of the bases are equal because the two bases of the prism are congruent. Okay, I'm just going to write, because they are, you guys know these symbols, congruent. You could translate the top base straight downward and it would match up the other. Again, if we were in class with things that we could touch and hold. Next question. How do the heights of the pyramids P1 and P3 compare? They are also equal. The heights of those two are equal because they are the height of the prism shown in the graph. If you look, they are both 4 units. How do the volumes of pyramids 1 and 3 compare? They are also equal. Because if the bases are equal and the heights are equal, we know that the volumes are equal. Let that sink in for a second. All right, next. Using the pyramids you built, compare pyramids 2 and 3. Think of the gray shaded triangles as the bases of the pyramids. I'm staring at them on my desk here in my office. You can't see them, and I apologize for that. These are formed by slicing one of the prism's rectangular faces down its diagonal. How do the areas of these two bases compare? I'm holding them up. I can actually put them together, and they are, wait, I lost it. Dark and dark. They are equal, okay? So the triangles match up, the bases are equal. The heights of the pyramids are equal because when assembled into the prism, the height lines coincide the lengths of the prism. How then do the volumes of the pyramids compare? They are equal. If the area of the bases are equal, they're both big B, and the heights are equal, then the volumes are equal. Okay, volume is big B times H. Number 3, based on your answers, how do the volumes of each pyramid compare to the volume of the prism? They're all 1/3 of the prism. Okay, the volumes of each pyramid are 1/3 of the volume of the prism. So we know that the volume of the prism equals big B times H. So the volume of the pyramid is 1/3 big B times H. Cool. That was what the goal was of today's lesson. Comparing cross sections, each solid in the image has a height of 6 units. The area of each solid's base is 10 square units. A cross section has been created in each by dilating the base using the apex, remember those are the apexes, as the center with a scale factor of 0.5. Calculate the area of the cross sections. Okay, if we have a scale factor of 0.5, I'm going to take the area of the base, and since we're talking area, what am I going to do with the scale factor? Okay, when I have a scale factor and I'm messing with area, I need to square the scale factor. So the area of the base is 10 times 0.5 squared times 0.5 squared. The area of the bases are all equal. So if I'm multiplying it by a scale factor of 0.5 squared, my answer will actually be 2.5 units squared. Okay, we don't have any measurements to get the areas of these slices, but we do know we have a scale factor and an area of the base. And when we do area, our scale factor is squared. Number 2, suppose a new cross section was created in each solid, all at the same height, using some scale factor K. How would the area of these 3 cross sections compare? Explain your reasoning. They would all be times 10 times some scale factor squared, because that's all we have to do is multiply it by the scale factor squared because we're dealing with area. Number 3, what does this information about cross-sections tell you about the volumes of the 3 solids? The cross-sections, all cross-sections at the same height have equal area, therefore the 3 solids all have the same volume. Okay, they are all equal volume because they all have the same height. They all have the same area of the base, and volume equals 1/3 big B times H. H's are all same, big B is all the same, 1/3 is 1/3, so the volume's all going to be the same. Calculate the volume of each of the solids. 1/3 area of the base times height, which was 6 units. 10 times 6 divided by 3 gives me 20 units cubed. This is your summary sheet. I didn't copy in the title because it got a little small. But this right here is all you need to know from what we learned today. Right there, area of the cross-section, B times K squared. The volume is 1/3 BH. Any pyramid or cone, doesn't matter. That's it. Good job. Please, text me, Google Hangout me, whatever you need to do to ask questions. I'm here from 8 until 4. All right, take care. Miss you guys.